Alright, in this video we are going to learn two things. The first thing we're going to do is we're going to review how to solve differential equations using the method of separation of variables that we talked about in the first part of 6.1. And we're going to spend most of our time learning about something called Euler's method, which is basically a method of how to approximate a particular solution to a differential equation. Alright, so let's review how to solve a differential equation. Well, example 1 here, if we have dy dx equals x plus 2, we're going to start by integrating both sides. And if we integrate dy dx, and we're going to integrate x plus 2, and the integral of dy dx is simply y, and the integral on the other side is going to be x squared over 2 plus 2x, and don't forget, if we do not have a lower and upper limit, then we need that plus c there. And this is called a general solution. Alright, this is called a general solution. General solution is when you don't have an initial value to plug in to get the c. Now, if they give you an initial condition, you can get a particular solution, and you get that by plugging in the initial value into the general solution. So we have this ordered pair 0, 1. So if we take that and plug it in to our equation, plug 1 in for y, we get 1 equals 0 squared over 2 plus 2 times 0 plus c. So c ends up being 1. And so our particular solution ends up being y equals x squared over 2 plus 2x plus 1. So far, you have been given differential equations that you are able to solve and get an equation for y. So for instance, in the previous example, you were able to actually get the differential equation to solve it, x squared over 2 plus 2x plus c, and I believe the c was 1. And you were able to find values like y of 1.5 and y of 3 by simply taking those x values and plugging them into the function. But let's suppose we gave you a differential equation like dy dx is equal to 2xy plus y squared. And you start to try to solve that by separating the variables. So maybe you'll pull out a y on this side and you end up with 2x plus y. And then maybe you'll divide both sides by y and multiply both sides by dx. And you end up getting dy over y is equal to 2x plus y times dx. And you realize you get stuck because you cannot separate all of the y's on the left side and all of the x's on the right side, and so you are not able to get a general solution. And if you can't get a general solution, you can't get a particular solution either, and so you're basically stuck. What do you do in these examples where you still may want to get an approximation of the y value when x is 1.5 or the y value when x is 3? For this, we're going to use a method called Euler's method. And Euler's method is a method that we use to approximate the particular solution given certain x values. We may not get the exact y value, but we can get an approximate value for these using Euler's method. And that's what we're going to do next. So in the example in the notes, we are given the differential equation dy dx is equal to 2x. And that actually happens to be a differential equation that we can solve by hand very simply, and I think we're given the initial condition 0, 1. So we can multiply both sides by dx, and we get dy to be 2x dx. We integrate both sides, and we end up with y equals x squared plus c. And if we plug in our 0, 1, we can see that c is going to equal 1. So this is our particular solution here, and we can graph that over here, and we can see that this is a parabola shifted up 1 unit. All right, and here is our point that we are given, 0, 1. So we're going to use Euler's method, and we're going to use Euler's method to approximate the value of f of 1. Now certainly we can see that the real value of f of 1 is simply 2 by just plugging in 1 into this equation over here, so we get 2. But what we're going to learn is how to use Euler's method to approximate that in the event that we are given a differential equation that we cannot solve, such as the case in the example before. All right, so we're going to go back to something we learned a long time ago. We're going to start with the slope between 2 points. So maybe we'll call this point here x0, y0. And we'll call some other point x1, y1. And so if we wanted to find the slope between those points, let's say we want to find the slope at 0, we would say y1 minus y0 over x1 minus x0. And if we multiply both sides by x1 minus x0, we end up getting x1 minus x0 times the slope at 0 equals y1 minus y0. And we can add y0 to both sides and rearrange it, so you end up getting y1 is equal to y0 plus the slope at 0 times x1 minus x0. And so what we notice here is that if we want y1, we can use the previous y value plus the slope at the previous point and the difference between the x values. All right, so we are going to apply this, and so you can visually see it. Basically what we're going to do is we are going to draw a tangent line at this point given, so we're going to have a tangent line there. And then our first point, we're going to use the slope on the curve to draw another tangent line essentially. And then whenever we plug in 1 into our tangent line, that is going to be an somewhat close approximation of the real value on the curve. All right, so let's do this in 2 different steps here. So we are looking for y of 0.5 first. So we'll say y of 0.5 is equal to y of 0 plus the slope at 0 times the difference in the x values. Well, that's just going to be when x is 0.5 minus when x is 0. So our y of 0.5, our approximation, is going to be the y value at 0, which is 1, plus the slope at 0. And if we want to figure out what that is, we would have to go back to here and plug in our x value. Our x value is 0. 0 times 2 is 0. So our slope is simply going to be 0 here times 0.5. So our approximation for the y value when x is 0.5 is 1. Now we're going to repeat that process again because the problem says we are to use 2 steps of equal size. So now we're going to do it again. So y of 1 is going to equal now the y value at 0.5, which we'll call y of 0.5, plus the slope at 0.5 times the difference between, well, 1 minus 0.5. This is called delta x. And in most of the problems that you're going to see, the delta x is going to be the same. Here you can see it's going to be 0.5 each time. So our y1 is equal to our y value at 0.5, which we approximated to be 1, so we'll throw that in there. Now the slope at 0.5, we need to use that x value of 0.5 and we need to plug it into our equation for the slope at any point, our differential equation. So if we plug in 0.5 times 2, we get 1. So the slope at 0.5 is 1, and you can see right here that the slope changes. All right, that's going to be the slope of our second tangent line there. All right, and then we have 1 times 1 minus 0.5, which is 0.5, and we end up getting 1.5. And this is our approximation for y of 1. And our real value, as we found earlier, the real y of 1 is 2. And the difference between them is called the error. So the error is the actual minus the approximated value. In this case, that's going to be 2 minus 1.5, which is 0.5. All right, now how would we get a better approximation? Well, just like in other things that we've done this year, to get a better approximation, we would use more steps, which would mean we would draw more tangent lines and get more points and slope. But most of the problems for the AP exam is going to be steps of size 2 or 3. All right, here is a perfect example of the value of the Euler's method right here. Because we are given a differential equation that we are not able to solve using algebraic methods. Watch, if you start with dy dx, and that's equal to x plus y, you may get the idea of subtracting y to bring it to the other side equals x. But the problem is when you multiply by dx all the way across, that may go from there, but now you still got a dx over on this side, and so you cannot separate all the x's on the right and all the y's on the left, so you are basically stuck. So essentially, we need to be able to find a way to approximate values on the particular solution, even though we cannot actually solve it for y. All right, so we are given an initial condition of 4 and negative 1. So maybe we'll write that down right there. And we want to estimate or approximate f of 4.2 using 2 steps of equal size. And on the AP exam, it's normally going to be 2 steps or maybe 3 steps, just to make sure you understand the process. All right. So if we are going from 4 to 4.2 using 2 steps, that means our delta x is going to be 1. Okay. And so our first goal is to approximate the y value at 4.1. And we're going to use the y value at 4 plus the slope at 4, and then our delta x is simply 1, the difference between, 0.1, and let me go back and fix that. It's going to be 0.1. All right, 4 to 4.1 and 4.1 to 4.2, 0.1. All right, so our y of 4.1 is going to be our y value at 4, which is negative 1, which they gave us right there. So negative 1 plus the slope at 4. Now we need to use our differential equation to do that. So dy dx is equal to x plus y, or 4 plus negative 1, which is 3. So our slope when x is 4 is going to be 3 times 0.1. And so we end up with negative 1 plus 0.3, which ends up giving us negative 0.7. All right, so that's our y value when x is 4.1. And now we're going to do that same exercise for the y value at 4.2. All right, so let's see what we get here. Y of 4.2. So actually, maybe we'll go back here and write our new ordered pair to be 4.1 and negative 0.7. And so now we'll come over here and we'll say y at 4.2 is equal to the previous y value, which is negative 0.7, plus the slope at 4.1, which we need to now find that out. So dy dx is equal to x plus y. So we're going to plug in 4.1 plus negative 0.7, which is ending up to give us 3.4. So this is actually going to be 3.4. So I'm going to erase that and put 3.4 in its place, times that same 0.1, which is the delta x. So we end up getting negative 0.36. And that is the approximate value on the curve when x is 4.2. All right, let's put it all together here. We should be pro at this by now. So we are given the differential equation dy dx is equal to x plus 2 and the initial condition of 0, 3. Find an approximation for y of 1 by using Euler's method with 2 equal steps. Sketch your solution. Okay, we'll worry about the sketch later. So we need to go from when x is 0 to when x is 1 using 2 equal steps. So our delta x is going to be 0.5. All right, so we need to first find y of 0.5, and maybe I'll write it like that this time. Y of 0.5 is equal to y of 0 plus the slope at 0 times our delta x, which is 0.5. And that is going to give us y of 0 is 3 plus the slope at 0. Well, our dy dx is x plus 2 and x is 0, so our slope is 2 times 0.5. And so that's going to give us 3 plus 1, which is 4. And then, so our ordered pair, we'll just call it 0.5 and 4. That is our approximate ordered pair. So now we need to find y of 1, and that's going to be equal to the previous y value, y of 0.5, plus the slope at 0.5, and this is where people sometimes will forget. It's not the original slope, it's the slope at 0.5 times that same delta x of 0.5. So let's see what we get. Y at 0.5 was approximated to be 4 plus the slope at 0.5. Okay, well, for this, we need to actually plug in 0.5 into our dy dx. All right, so if we plug in 0.5 in there, we will get 2.5 as our slope. So that's going to be 2.5 times 0.5, which is our delta x. So when we work this all out, we end up getting 4 plus 1.25, so 5.25. And that is our approximation for y1. Okay, this is an approximation. All right, so now we go to letter B, and we actually want to solve this differential equation, and we want to get a particular solution. And we're given the same initial conditions, 0, 3. So we want to solve this. So we're putting it all together in this particular problem here. So if we solve it, we're going to solve it by taking the integral of both sides. So dy dx is equal to the integral of x plus 2. We've seen this earlier. And this is going to give us y equals x squared over 2 plus 2x plus some constant. And when we plug in our initial condition 0, 3, we end up getting a particular solution of y is equal to x squared over 2 plus 2x plus 3. And now it's asking us to use our solution to find the actual value. So this y1 that we're getting ready to find is the actual value. What we found in part A was the approximate value. So let's go ahead and plug in 1 and let's see how close we get. Alright, this should actually be a squared right there. So 1 squared is 1 over 2, and 2 times 1 is 2 plus 3, and we end up getting 5.5. Alright, not bad. Our approximation was 5.25. Our actual solution is 5.5. And part C, we can see that the error in using Euler's method is the difference between the approximate value and the exact value, or the actual value. So what was the error in our answer? Well, it was 5.5 minus 5.25. So our error was pretty good. It was 0.25. And how could you produce a smaller error using Euler's method? Well, we would use more steps. You'd use more steps. If you draw more tangent lines, you'll get a much better approximation. And that essentially is Euler's method. So we will do some examples tomorrow in class.